Hello everyone, welcome to Gnana Deeksha, concept-based digital learning. I am Nirmala Hrudaya, lecturer in chemistry, TSWRDC, Jagitiyal. So my topic is on photochemistry. Before entering the topic, I would like to know some of the common examples which we encounter in our day-to-day life, like fluorescent bulbs, fluorescent tapes, glow sticks, glow bands, radium stickers, highlighters, luminescent dials in watches, and even warning signals in the traffic. Zinc sulfide in chemistry also glow in the dark. Now, how does that happen? It's all just because of the most important concept related to chemistry, that especially photochemistry. Now, I will make you understand those phenomena. To start with, what exactly the photochemistry is. So, it is a branch of chemistry which studies the effect of radiation, particularly UV visible radiation on the molecules. Some of the examples of the photochemical reactions include photosynthesis, where the plants will be able to synthesize food material in the presence of sunlight. And one more example is human formation of vitamin D by exposure to sunlight, and bioluminescence. So here the organisms will be able to produce light by using a chemical reaction taking place in the abdomen region. And formation of ozone. So these all reactions take place in the presence of light. So what is light? Light is an electromagnetic radiation which consists of both electric component and magnetic component vibrating perpendicular to each other when it propagates from one place to another place. It consists of different range of radiations depending upon which it is again classified into several regions like gamma rays, X-rays, UV visible, infrared, microwave and radio waves, which is shown in the figure. So, in the figure, as we move from the left to right, that is from radio waves to gamma rays, the wavelength decreases and each of these radiations has got its own impact on the molecules when they interact. So, in the molecule, there are different molecular energy levels present. In molecules, that particular energy level, we say it as quantized. So, there are three types of electronic energy levels present in the molecule. Those are electronic energy levels, vibrational energy levels, and rotational energy levels. This figure explains about the arrangement of different energy levels in the molecule. The energy gap between the electronic energy levels is more, which is designated as S0, S1, S2, and so on. In between the electronic energy levels, vibrational energy levels are present, and in between the vibrational energy levels, rotational energy levels are present. That is, the energy required for the electronic transitions is much more compared to the vibrational and rotational transitions. So, molecule interacts with this electromagnetic radiation and undergo different changes accordingly. As you can see, when UV visible light interacts with the molecule, and that is able to dissociate bonds present in the molecule. Whereas, if the IR radiation interacts with the molecule, that will be able to bring the vibrations of the bonds present in the molecule, from which we can extract the information regarding the different functionalities present in the molecules. And when the microwave interacts with the molecule, that will be able to rotate the bonds present in the molecule, from where we can get the information regarding the bond lengths and bond angles. The photochemical reactions occur mainly in two steps. Step 1, which is also called as primary process, where the activation of the molecules takes place by radiation with the light. And the second step, which is also called as secondary process, where the activated molecules get converted into products. Here, I have mentioned the example of the formation of ozone molecule, where in the primary process, the oxygen gets radiated with the light and becomes activated, followed by the formation of ozone in the second step. The entire photochemistry is mainly governed by two important laws. Those are laws of photochemistry. First law is called as Rother's law, and second law is called as Stark-Einstein's law. Here is the Grother-Stopper's law. That is, only the light that is absorbed can produce the photochemical change. In other words, we can say that the absorption of the light is highly specific. And this law is also called as law of photochemical activation. Coming to the second law, which is called as Stark and Fink's law, which tells us that the molecules absorb a single quantum of light is becoming excited. That means each molecule undergoing excitation will require one photon of energy. That means if my compound contains 100 molecules, for the excitation of those 100 molecules, it requires 100 photons of energy. So this law is called as law of photochemical rings. Whether all the molecules that are being activated in the primary process, are they getting successfully converted into products? Maybe yes or no. That can be measured by a parameter called as quantum yield. So quantum yield is a parameter which is used to measure the efficiency of a chemical reaction, or we can say efficiency of a photon emission. And it is given by the formula number of molecules that are decomposed, or the number of molecules that are successfully getting converted into products by the number of photons that are absorbed. So here the quantum means may be equal to 1 or may be less than 1 or may be greater than 1. So what if the quantum is equal to 1? We can say if the quantum is equal to 1, then we can say that particular reaction is having good quantum yield. When a reaction is said to have a good quantum yield, when the quantum yield is equal to 1. So when it becomes equal to 1, means the number of molecules that are decomposed will be equal to the number of photons that have been absorbed. That means no photons have been wasted. That means all the molecules that are excited by the absorption of photons have successfully got converted into products. The best example for the quantum yield, good quantum yield, is SO2 plus Cl2 gives rise to SO2Cl2, formation of sulfonyl chloride. Coming to the low quantum yield, where the pi value is less than 1. So when this occurs, when the number of molecules decomposed is less than 1 per photon, that means all the molecules that are being activated in the primary process are not getting converted into the product. Some of the molecules are coming back to the ground state without successful formation of the product. That means number of absorbed photons have been wasted. There may be various reasons for the low quantum yield, like the deactivation of the activated molecules before they form products, collision with the non-excited molecules, reversible primary process, or whatever the fragments that are formed in the primary process are again recombined to form the substrate molecules without the formation of product molecule. Example for the low quantum is dimerization of anthracene, whose quantum is found out to be 0.5, where the 2 moles of anthracene in the presence of light will form dianthracene molecule. One more example is photochemical combination of H2 and Br2, whose quantum is found out to be 0.01, which is nothing but 1 by 100. That means out of 100 photons observed by the molecules, only 1 molecule is successfully got converted into products. Next is high quantum yield. So when we can say a particular reaction is having high quantum yield, when the number of molecules decomposed is greater than 1 per photon. That means only 1 photon is absorbed by so many number of molecules are getting successfully converted into products. The reasons for this type of quantum yield may be chain reactions, or sometimes the reactions are exothermic, means the heat is evolved in particular step of the reaction, and formation of intermediate products acts as a catalyst for the next step of the reaction. One more example is formation of HCl. whose quantum field is found out to be 10 to the power of 4 to 10 to the power of 6. That means with 1 photon of energy, almost 10 to the power of 4 molecules have been getting converted into products. The reason behind this is chain reaction. We can see initially the chlorine in the presence of light will undergo dissociation into chlorine radicals. So this is called as chain initiation step. And the chlorine radicals which were formed in the chain initiation step will further undergo reaction with the HCl and will enable the chain to undergo propagation. And the next two steps are called as chain propagation step. When this reaction is going to end, when the two chlorine radicals again combine to produce Cl2 molecule. And this step is called as chain termination step. So termination takes place by the decombination of the chlorine radicals to form the chlorine molecule. The quantum yield of this reaction, as I said, is equal to 10 to the power of 4 to 10 to the power of 6. As we already discussed, there are different electronic energy levels present in the molecule, and these electronic energy levels contain electrons. Depending upon the spin orientation of the electrons present in the molecular energy levels, again these energy levels are classified into singlet, doublet and triplet states. And this phenomenon of calculating the spin orientation is called as spin multiplicity, which is calculated by the formula J is equal to 2s plus 1. S is the total spin of the electrons present in the particular molecular orbital. Coming to the singlet condition, when we say a particular molecular orbital is in singlet condition, if J value comes out to be 1, so when J value comes out to be 1, if the molecular orbital contains 2 electrons with opposite spin, and this occurs in the case of sigma bonded electrons. Now, coming to the doublet, if J value is equal to 2, that particular molecular orbital is designated as doublet, and this occurs when there is unpaired electron present in the molecular orbital, and this is mainly seen in the case of free radicals. If J value is equal to 3, then we say that particular electronic energy level is in spin multiplicity triplet. When this occurs, then if the molecular orbital contains 2 electrons having parallel spin, then we say that particular molecular orbital is in triplet condition. So, until now, what we get to know is on irradiation of the molecules, they will get excited from the ground state S0 to higher singlet states like S1, S2 and so on, and becomes activated in the primary process. And from there are 3 possible ways for those activated molecules. That is, they can either get converted into products or they de-excite and get converted into triplet states having lower energy, or they may de-excite to the lower energy singlet state. So, the de-excitation of the molecule without formation of the product is termed as photophysical process. Now, what this photophysical process is? The photophysical processes are those which are taking place without any chemical change involving in the systems. As we discussed in the before slide, that there are 2 types of photophysical processes. That means there are 2 parts for the de-excitation of the activated molecules. One is thermal decay, other one is radioactive decay, which is well explained by using the Jablonski diagram. Now, the thermal decay is again classified into 3 types like vibrational cascade, internal conversion and intersystem process, whereas the photochemical decay is again classified into fluorescence and phosphorescence. The thermal decay is a condition where the molecules de-excite from the higher energy level to lower energy level by release of energy in the form of heat. So such processes are also called as non-radiative processes. Whereas in case of photochemical decay, where molecules undergo de-excitation coming from the higher energy levels to lower energy levels by emission of energy in the form of light. This is a radiative process. Now the Jablonski diagram explains very well about various photophysical processes. So what is a Jablonski diagram? So before explaining the Jablonski diagram, I would like to explain different electron energy levels which are designated as S0, S1, S2 and so on. This means that they are singlet states. Here you can also see there are triplet states corresponding to S1 and S2, T1 and T2. In between this electronic energy levels, there are different vibrational energy levels present. Now in the first step, what happens? The transition of the molecule takes place to the higher singlet state from the ground state singlet state by irradiation with light. This step is called as activation. And now let us assume that the molecule is in S2 level and that molecule returns to the ground state by any of the following paths. Path 1. The molecule may lose energy in the form of heat and return from higher vibrational energy level to lower vibrational energy level of same singlet state. So this is called as vibrational cascade and this is a non-radiative process. Path 2. The molecule will de-excite from the higher singlet state to lower singlet state by the emission of energy in the form of heat, and this is again a non-radiative process which is also called as internal combustion. Path 3. Some energy may be lost in the transfer from higher energy singlet state to lower energy triplet state in the form of heat, and it is called as intersystem crossing. This process mainly involves in the transition between states of different spins, different multiplicity, which means that the molecule has to change the spin of the electron while undergoing transition between singlet to triplet state, and this path is also a non-radiative process. Next, path 4. After intersystem crossing, the molecule may again choose a path to lose energy in the form of light in going from the excited triplet state to ground state singlet state. So this is called as phosphorescence and this is a radiative decay. In this process also the molecule needs to change its spin from higher triplet to singlet ground state. So it is a delayed process. Path 5. If the molecule returns from higher singlet state to lower singlet state by the release of energy in the form of light, this is called as fluorescence, which is a spontaneous process as there is no need to change in the spin of the electron. Now, the exact difference between the fluorescence and phosphorescence is made clear. That is, fluorescence in certain substances when exposed to light are certain other radiations absorb the energy and then immediately start re-emitting the light. Such substances are called as fluorescent substances and the phenomenon is called as fluorescence. Examples: organic dyes such as kerosene, fluorescence, vapors of sodium, mercury, iodine, etc. will fluoresce in the presence of UV light. Phosphorescence. There are certain substances which continue to glow even after some time the external source is cut off. Thus, phosphorescence is also called as slow fluorescence. All glow in dark toys exhibit phosphorescence phenomenon. Here, the well-explained Jablonski diagram. So first step is excitation step where the molecule will enter from ground singlet state S0 to higher singlet state. Second one is vibrational cascade where the molecule enters from singlet higher vibrational level to lower vibrational level of the same singlet state. So here spin multiplicity is maintained. Such condition or such process is called as vibrational cascade. If the molecule de-excites from higher singlet state S1 to lower singlet state S0 by the release of energy in the form of light, and that phenomenon is called as fluorescence. And fourth step is if the molecule is returning from the higher singlet state S1 to ground singlet state S1, liberating energy in the form of heat, that is called as internal conversion. And if the molecule is changing its spin multiplicity from S1 to T1 and giving energy in the form of heat, such process is called as intersystem crossing. If the molecule de-excites from the excited triplet state to ground triplet state of the same vibrational energy level maintained, and such process is also called as phosphorescence. If the molecule de-excites from the higher triplet state to ground state singlet state with the emission of energy in the form of light, and such process is called as phosphorescence. Now, why one should employ the photochemistry? Overcome, because in order to overcome the large kinetic barriers in a short time, and also produce an immense complexity in a single step, as in the case of chain reaction of HCl, formation of HCl, and also form the thermodynamically disfavored products. And moreover, the reagent is cheap, easily accessible, and renewable source of energy, that is nothing but light. Now, what are the application parts of the photochemistry? The one most important application is photodynamic therapy. It is one of the most important biomedical applications, where it is a two-stage treatment that combines light energy with a drug called photosensitizer, which is designed to destroy the cancerous and precancerous cells after light activation. Photosensitizers are the objects which are activated by a specific wavelength of light energy, usually from the laser. Coming to the optical brighteners, these are fluorescent compounds which absorb invisible UV radiation and transform it into visible blue fluorescent light. This is how optical brighteners work, and these are designed to brighten the color in paints, films, plastic, and fibers, which will give them a fresher look. Coming to the third application, fluorescent dyes. In this dye, short wavelength is converted into longer fluorescent light in the visible spectrum, and these dyes are encountered as a luminous colors in advertising hoardings, shock colors in fashion causing whitening effect, and also warning colors in traffic. Fluorescent dyes also have property of emitting twice as much as light at the longer wavelength as is contained in the incident light. Fluorescent lamp. The phosphor. It is an object which will emit light after getting exposed to some radiation. So, in fluorescent lamps, the phosphor pores inside surface of the fluorescent lamp absorb UV light, and that is emitted by the mercury atoms present inside the bulb. It then re-emits ultraviolet rays, but at the longer wavelengths as visible light. A fluorescent lamp gives off much of more light than incandescent one, and does not produce heat. Detecting artificials. A black light, which is also called as UV light because it contains a seedy bluish purple glow, is actually an ultraviolet lamp and brings out the vibrant colors in the fluorescent materials. For this reason, it is useful in detecting art forgeries. Newer paints tend to fluoresce when exposed to ultraviolet light, whereas older paints will not. Thus, if a forger is trying to pass off a painting as the work of old master, the ultraviolet lamp will prove whether the artwork is genuine or not. Rubies and lasers. A ruby, when exposed to blue light, will absorb the radiation and go into excited state. After losing some of the absorbed energy to the internal vibration, the ruby passes through a state known as metastable state before dropping into what's called as ground state, the lowest energy level of an atom. At that point, it begins to emit radiation on the red end of the spectrum. So the laser is a very narrow and highly focused monochromatic beam of radiation which is being used for everything, right from etching data on the surface to perform in the eye surgery. Television tubes. So television tubes mostly rely on the phosphorescence phenomenon. The tube itself is coated with the phosphor material and narrow beam of electrons causes excitation in a small portion of the phosphor. So the phosphor, what it does, then it emits red, green and blue light colors that are primary colors of the light and continue to do so even after the electron beam has been removed onto the other region of the phosphor. So as it scans across the tube, the electron beam is turned rapidly on and off, creating an image made up of thousands of glowing and colored dots. The next important application of the photochemistry is the fluorescent and phosphorescent stamps are used for automatic sorting of letters and postcards. Next one is making dials and light switches in the watches. Since the glow in dark has found various applications. Now the most important application of the photochemistry is cosmetic sunscreens. Here also the phenomenon fluorescence is being used. The function of a sunscreen cosmetic is to filter the solar radiations. So the rays that are most responsible for the erythema, that means skin rashes, are filtered out, and those that tan direct are allowed to pass through the unhindered. Thus an attractive tan is obtained without any sunburn. So this is regarding the applications. Concluding, I would like to take the summary of whatever we have discussed today. So, what we have learned? First one, what is photochemistry? What are the examples of photochemistry? And what is light? We have seen that light is an electromagnetic radiation, consists of different regions. So, when light interacts with the molecules, what are the changes that are going to take place in the molecule, and what are the applications each light is going to bring out when that particular light interacts with the molecule. And next one is what are the different energy levels present in the molecule and how they are designated as singlet, triplet states, and how it is explained when the molecule undergoes excitation in the primary process, in the secondary process, that excited molecule getting converted into products. And what are the two laws of photochemistry? Now, how the two laws are going to be applied in determining the quantum yield of the molecule. So, what is quantum yield? Quantum yield is a parameter which is used to measure the efficiency of the chemical reaction. And we have seen various chemical reactions that are having good quantum yield, less quantum yield, and more quantum yield. Coming to the photophysical process, we have seen that two important photophysical processes like radioactive decay and thermal decay. So, radioactive decay is a process where the de-excitation of the molecule takes place by emission of energy in the form of light. In thermal decay is a condition where the de-excitation takes place by the emission of energy in the form of heat. And in thermal decay we have learned what is vibrational cascade, what is internal conversion, what is intersystem crossing. The photochemical decay we have gone through fluorescence and phosphorescence, which has got varied applications in the field of science and technology. And the Jablonski diagram has very well explained all these photophysical processes. The fluorescence and phosphorescence concepts are two different concepts. Here, the fluorescence we have seen that it is a spontaneous process and phosphorescence is a non-spontaneous process since it requires change in the spin of the electron. Whereas the fluorescence is a spontaneous process where there is no need for change in the spin of the electron. So, this is what we have learned today. And thank you one and all. And thank you for giving me this opportunity. Stay home, stay safe.